These days, the diesel engine propels most of the tonnage of all of the world's shipping. Given good care, the diesel engine provides maximum effect on minimum oil consumption. The engineer will see to that. At the moment, he's checking the temperatures of the exhaust gas and the cooling water. To make a further study of the diesel engine, we leave the engineer and his instruments and put sight glasses on the engine from top to bottom. This reveals the movable parts: pistons, piston rods, crossheads, and connecting rod and crankshaft. This sectional view shows the functions which the most important parts of the engine have to perform. In the upper part of the cylinder, an amount of fuel oil is burned, which causes the temperature, and thus the pressure, to rise in the combustion space. The gas pressure acts on the piston, from which the force is transmitted through the piston rod and the crosshead to the connecting rod, and results in a torque. The thermal energy has been converted into mechanical energy. In any given piston position during the working stroke, the crosshead is exposed to a vertical force from the piston rod and a force in the direction of the connecting rod, which together result in a horizontal force. This horizontal force must be transmitted to the engine frame, and for this purpose the crosshead is provided with slide shoes supported on vertical surfaces, the guide bars on the engine frame. Powerful forces are at work in a big marine engine, and accordingly the engine parts are of major dimensions. To provide sealing against the high pressures, the piston is fitted with piston rings. The rings are fitted by means of a special tool which evenly distributes a bending moment to the rings, thus preventing the danger of a permanent deformation. On some engines, the crankshaft is so big that to facilitate manufacture and installation, it's made in two halves, which are later bolted together. Each half is built up from a number of main bearing journals, crank webs, and crank pins. Let's look a little closer at the principle on which a two-stroke engine works. Fresh air is supplied by a turbocharger. From the turbocharger compressor, it's conducted through air coolers into a common scavenge air receiver along the engine and to the scavenge air space around each cylinder. When the piston approaches the end of the downstroke, the exhaust valve opens, the scavenge air ports are uncovered, and fresh air flows up through the cylinder. Exhaust valve and scavenge air ports are then closed, and during compression the air is heated, causing the ignition of the injected fuel. The combustion increases the temperature and thereby the pressure, which drives the piston downwards. The exhaust valve opens, the pressure falls, and the combustion products are expelled while fresh air flows in. The air is again compressed, fuel is injected, ignited, the gases expand, the exhaust valve opens, then the scavenge air ports, the cylinder scavenged, and the cycle is repeated. The power developed by an engine depends on the pressure sequence in the cylinder. The output of an engine is dependent on the relation between pressure and volume in the cylinder during compression, combustion, and expansion. For each separate cylinder, the gas process could be described by a curve, the so-called PV diagram or indicator diagram. The diagram shows that the pressure is almost equal to the scavenge air pressure when the scavenge ports are uncovered. The exhaust valve and scavenge ports are then closed, the air is compressed, and when the fuel is injected and ignited, the pressure will rise rapidly and remain at maximum during continued injection. After injection, the pressure in the cylinder falls to exhaust pressure and, during the exhaust period, to scavenge air pressure. Scavenging, compression, combustion, expansion, exhaust, and back to scavenging. The power developed by an engine depends on the pressure events in the cylinder. The pressure events can be recorded by means of an indicator connected to an outlet from the combustion space. The combustion chamber pressures can be measured by a PMI system supplied from MAN diesel. The PMI system replaces the traditional indicator and indicator drive. The PMI system allows the engine operator, through high qualitative data collection, to further refine the performance and reliability of the diesel engine. Essentially, the PMI system ensures that the load and balance of cylinders is kept within predefined limits with regards to their mean indicated and maximum combustion pressure. The PMI system is designed to produce reliable calculation of mean indicated cylinder pressure and other performance data that require the accurate pressure measurement of cylinder pressures and detection of the crankshaft position. From the indicator diagram, the so-called indicated output can now be computed. At any given piston position during the compression stroke, there's a certain pressure, P, acting on the piston top, if the piston travels a short distance further, corresponding to delta V, and if we ignore the minimal change in pressure, the amount of work done, delta A, will be given by the pressure multiplied by the change in volume, or P times area below the part of the compression line corresponding to delta V, and the same applies to every single part of the compression curve. That's to say that the whole area below the compression line represents all the work that the piston must perform to compress the air in the cylinder. During the expansion, the piston pressure acts in the same direction as the piston's moving, so the piston receives an amount of work. And it'll be seen in the same manner as before, that the amount of work received is represented by the area below the expansion curve. The amount of work transmitted to the piston during a full engine revolution must therefore be the difference between that delivered during the compression and that received during the expansion. In other words, it's given by the area between the curves. Thus, A equals sigma P multiplied by delta V. The equation can be rearranged to express the temperature T, direct for an arbitrary piston position. The indicator diagram gives us the values that are to be substituted in the equation when computing the temperature. For the top position of the piston, we find the temperature to be about 890 degrees Kelvin. The highest temperature occurs at the cessation of combustion, here found to be 1900 degrees Kelvin. In this way, the whole of the temperature curve can be calculated right up to the moment when the exhaust valve opens. To get a better idea of what's happening, we'll measure in degrees centigrade instead of degrees Kelvin. Already during compression, the temperature reaches the melting point of lead. During the first part of combustion, the temperature reaches the melting point of aluminium. Shortly after that, the temperature reaches the melting point of cast iron. The high temperatures in the cylinders even exceed the melting point of steel. Combustion takes place so quickly, however, that there's no time for the high temperature to be transferred to the cylinder wall. The temperature of the metal surfaces will not exceed the mean temperature of the process, about 620 degrees centigrade. Then again, the cylinder's made of cast iron, which begins to lose its strength at already around 300 degrees centigrade, besides which the lubricating oil will lose its lubricating ability if it becomes too hot. It's therefore necessary to provide efficient cooling, partly with oil led through the piston rod up into the piston itself, and partly with water circulating through the cooling jacket around the cylinder and cylinder head, and passing rows of narrow drill channels placed close to the most heavy, heat-loaded internal surfaces. If a cooling water outlet temperature of about 80 degrees centigrade is maintained, we can prevent the temperature on the inside of the cylinder wall from exceeding 300 degrees centigrade. This is possible because there's a drop in temperature as the heat passes from cylinder gas to metal. Even though the gas is in violent motion inside the cylinder, the boundary layer close to the wall forms a rather effective insulating layer where the temperature falls rapidly. Through the wall itself, the temperature falls evenly, but the heat transfer to the cooling water is controlled by the local boiling point of the water in contact with the wall, the so-called microboiling phenomenon. The high wall temperature causes a local boiling, which is able to absorb relatively large amounts of heat. Small steam bubbles are formed, which immediately break loose from the surface and condense in the surrounding water. Due to this, the wall temperature is almost independent of the transmitted amount of heat, provided that the water temperature is safely below its boiling point. With a mean gas temperature of about 620 degrees centigrade and a cooling water temperature of about 80 degrees centigrade, it's possible to calculate a thickness of iron that offers the same resistance to heat flow as the boundary resistance between cylinder gas and cylinder wall, and similarly a thickness of iron that corresponds to the boundary resistance between cylinder wall and water. As the drop in temperature through the entire homogeneous iron wall will occur evenly, the temperature of the original cylinder wall can be determined. 3 temperatures, which are calculated for the hottest point in the cylinders, explain why the material cylinder walls are able to withstand the high combustion temperatures. The process description shows that the combustion in the cylinders occurs within a fraction of the time of a revolution. Within this fraction of a second, defined by the flashes, about 100 grams of oil must be burned. A strong mixing of oxygen-rich cylinder gas into the oil, the so-called atomization, is a condition for the short time of combustion. Without a reasonable pump pressure level, mixing fails and the oil will not ignite at all, even though the stream passes right through a flame. If the pump pressure is raised to 80 bar, the oil is more finely mixed with air, but not enough to ensure reliable ignition. To illustrate this, an experiment set up with a pressure chamber and a high-speed film camera taking 3,000 pictures per second, showing how the mixing of gas into the oil is dependent on the friction between oil droplets and air molecules at a pump pressure of about 200 bar. First, a vacuum is created in the pressure chamber, and the high-speed camera shows the appearance of the narrow jet, which has an almost unchanged speed before it hits the bottom of the chamber. Then the vacuum is succeeded by a pressure of 3 atmospheres, and the high-speed camera registers the normal fuel jet with a wider spray angle showing the result from the friction between air and oil that's injected under high pressure. Furthermore, it can be seen that the velocity of the injected oil slows down as it passes downwards of the jet. Returning to the ignited injections and using a pump pressure of about 200 bar, the atomization is now so good that all injections are ignited. At the same pressure and continued injection, a flame is formed, but the flame soon dies out because of the lack of oxygen at atmospheric pressure. In order to compensate for the much lower pressure compared to the cylinder compression conditions, air is now admitted through the pipe in the lower part of the picture, allowing the flame to keep burning. The flame is formed some distance from the nozzle. The distance between the nozzle and the flame is about 400 millimeters, at which point the turbulent flame speed is in balance with the speed of the jet, as could be seen in the pressurized chamber. Inside a working diesel cylinder with more dense air, all these processes are more intense and shorter distances are required. The MAN diesel-developed, electronically controlled ME-type engine is the solution to the demand for reliable flexibility and any future regulations on emissions. The ME engine concept consists of a hydraulic mechanical system for the activation of fuel injection and the exhaust valves. The actuators are electronically controlled by a number of control units, forming the complete engine control system. MAN Diesel has specifically developed both the hardware and software in-house in order to obtain an integrated solution for the engine control system. The basic safety philosophy is that a single failure mustn't cause the engine to become inoperative. The control units in the engine control system are therefore duplicated. In the hydraulic system, normal lubricating oil is used as the operating medium. It's filtered and pressurized by a hydraulic power supply unit. The fuel oil pressure boosters have the same function as the fuel pumps on the conventional MC engine. However, the fuel injection plunger on the ME engine is driven by a hydraulic piston activated by control oil from an electronically controlled valve. The exhaust valve has the same function as on conventional engines. However, the exhaust actuator on the ME engine is driven by a 2-stage hydraulic piston activated by control oil from the fever valve. The exhaust valve is closed by the air spring as on the MC engine. The electro-hydraulic control system of the ME engine replaces the following components on the conventional MC engine. Chain drive for camshaft, camshaft with fuel cams and exhaust cams, fuel pump actuating gear, including roller guides and reversing mechanism, conventional fuel injection pumps and VIT system, exhaust valve actuating gear and roller guides, engine-driven starting air distributor, electronic governor with actuator, regulating shaft, engine side control console, mechanical cylinder lubricators. The new electro-hydraulic control system of the ME engine comprises HCU, hydraulic cylinder unit, including FIVA, fuel injection valve, fuel oil pressure booster, exhaust valve actuator, and electronically controlled alpha lubricator. HPS, hydraulic power supply unit, control units forming the complete engine control system. The starting air valves are opened pneumatically by electronically controlled on-off valves, which replace the mechanically activated starting air distributor. The crankshaft position is continuously monitored and transmitted to the control system. By controlling the electronic valves in relation to the crankshaft position, the engine control system fully controls the combustion process. System flexibility is obtained by means of different running modes. These are selected either automatically to suit specific operating conditions or manually by the operator to meet specific goals such as low fuel oil consumption or limited exhaust gas emission. The main operating panel, placed in the engine control room, is the interface for the engineer and operating engine. The MOP communicates with the engine control system and gives the operator an overall view of the engine condition during voyage and standstill. The alarm list in the MOP panel provides detailed information which assists the engineer in tracing and remedying any abnormal conditions in the ME control system. The engineer's still on the job, securing a long life for his engine by checking and testing, and most of all, by knowing the meaning and function of every little detail of his MAN B&W diesel engine.